When looking at time dependent problems, we solve for electric and magnetic fields for plane waves where there were no sources. Now, we will include sources and see how time dependent fields are generated and how they evolve with time. So, for next couple of weeks, I am going to cover inhomogeneous wave equation, then retarded potentials. So, for this, let us start by looking at the Maxwell's equations with sources, not in any medium, but vacuum. So, these equations are divergence of E is rho r, and it is a function of t. I am writing this explicitly over epsilon 0. Then I have curl of E equals minus dB dt. Curl of B remains 0 and divergence of B remains 0, and curl of B is equal to mu 0 j r and t plus mu 0 epsilon 0 d dt. So, let us look at, if I develop these equations into wave-like equations starting from the fields, how do they look? So, let us start with the electric field equation. If I take the curl of E, I can write this as minus, exchanging the space and time derivatives. I can write this as time derivative of curl of B. The left hand side gives me gradient of divergence of E minus Laplacian of E, and the right hand side is going to give me minus mu 0 dj dt minus mu 0 epsilon 0 d2E by dt square. Let us take the wave equation like terms on one side and write this equation as del square E minus d2E by dt square 1 over c square, where 1 over c square is mu 0 epsilon 0, is equal to gradient of divergence of E. So, that is rho r t upon epsilon 0 plus mu 0 dj r t dt. Look at this equation, the right hand side, the inhomogeneous term in the equation. It's quite involved. It has all the derivative, time, derivative with respect to space. Whereas, if you compare this with the plane wave equation without any sources, that was very simple, which was the wave equation equal to 0. So, you have to find a better way of handling the inhomogeneous term. In the same way, if I look at curl of B, this will be equal to mu naught curl of J plus 1 over c square d by dt of curl of E. This gives me the equation Laplacian of B minus 1 over c square d2b over dt square is equal to minus mu 0 curl of JRT. Again, if you look at the right hand side, it is involving derivatives of the current, not something we want to deal with all the time. So, therefore, we formulate this entire problem where sources are involved in terms of potentials. We had already done that in week 7, and I'll just write the equations and expect you to recall them, or go back if you don't recall them and learn them all over again. So, the equations that we had derived were in terms of the vector potential A RT and the scalar potential phi RT, and the equations were del square A minus 1 over c square d2A by dt square minus, and I am going to write this term in a different color, gradient of divergence of A plus 1 over c square d phi dt is equal to minus mu 0 j r t, and the equation for scalar potential was del square phi r t plus d by dt of divergence of A is equal to minus rho r t over epsilon 0. These are the two equations in terms of potentials, and then we invoked the gauge condition and chose in the Coulomb gauge del dot A equal to 0. That gave me for the scalar potential del square phi r t equals minus rho r t over epsilon 0. So, this equation gives you the answer which is looks like instantaneous, and for the vector potential I got del square A minus 1 over c square d2A by dt square is equal to minus mu 0 j perpendicular. And in the Lorentz gauge, we chose del dot A plus 1 over c square d phi by dt to be 0, and the equations then looked symmetric, and we had for the scalar potential del square phi r t minus 1 over c square d2 phi over dt square. There is a c square here, is equal to minus rho r t over epsilon 0, and for the vector potential del square A minus 1 over c square d2A by dt square is equal to minus mu 0 j r t. Before we proceed further, I want you to recall something, and that is what is j perpendicular r t. It is easier to work with Lorentz gauge when we want to see the two potentials and the radiation. So, I will be working in that gauge. We will be solving these equations for general rho r t and j r t in the future. In this lecture, I want to start with a simple problem, and that problem is that of a charge moving with constant velocity. So, the equations that I want to solve are del square phi minus 1 over c square d2 phi over dt square equals minus rho r t over epsilon 0, and del square A minus 1 over c square d2A by dt square equals minus mu 0 j r t. For a point charge q moving with constant velocity, v. To make life easy without any loss of generality, we will take V to be Vx. So, the particle is moving in the x direction. And at time t equals 0, it passes the origin. So, this is a problem I want to solve, the scalar and the vector potential for this particle moving with uniform velocity. So, very clearly the charge density rho RT is equal to Q delta function x minus Vt delta y delta z, and the current density J RT is going to be equal to Q V delta x minus Vt delta y delta z in the x direction. And I want to solve these equations with these sources. So, let us see how do the equations look now. So, I am going to have del square phi minus 1 over c square d2 phi over dt square equals minus 1 upon epsilon 0 q delta x minus Vt delta y delta z, and del square A minus 1 over c square d2a by dt square equals minus mu 0 q v delta x minus Vt delta y delta z in the x direction. The solutions that we are going to discuss were obtained by Lorentz and they are very simple to do in this case. So, I am looking for the solutions of these equations. Del square phi depends on r and t both, minus 1 over c square d2 phi over dt square, which I will now write in extended form, d2 phi over dx square plus d2 phi over dy square plus d2 phi over dz square minus 1 over c square d2 phi over dt square. I am writing it in this form because you will see that x minus Vt term is that traveling term that we encountered in solving the wave equation, and this equals q delta x minus Vt delta y delta z. Right now, let me just focus on the scalar potential, then we will come to the vector potential. So, now I can transform this easily using my wave equation knowledge and write x minus Vt to be a new variable alpha, and therefore, I can write this whole equation as d2 phi over d alpha square plus d2 phi over dy square plus d2 phi over dz square minus v square over c square d2 phi over d alpha square equals q delta alpha delta y delta z. So, I have transformed this equation into an equation with alpha, y and z, new space variables or new mixed variables. So, this equation then becomes 1 minus v square over c square d2 phi over d alpha square plus d2 phi over dy square plus d2 phi over dz square equals q delta alpha delta y delta z. Define 1 minus v square over c square as equal to 1 over gamma square, and I'll also use the notation beta equals V over C. You can see I'm using the notation which is used in relativity. Then I can write this whole equation as d2 phi over d gamma alpha square plus d2 phi over dy square plus d2 phi over dz square equals q delta alpha delta y delta z. Now, let us define this gamma alpha to be a new variable, let us say zeta, so that delta alpha will be delta zeta over gamma, which is equal to gamma delta zeta, and this equation then becomes d2 phi over d zeta square plus d2 phi over d y square plus d2 phi over dz square equals minus q delta zeta delta y delta z. I have been missing this minus sign all over, so let me just correct this right here on the left hand side and this right here on the side. So, what do we have now? The equation that we have is d2 phi over d zeta square plus d2 phi over dy square plus d2 phi over d z square equals minus q gamma delta zeta delta y delta z. Let me see if I put gamma on the previous slide. There was a gamma missing here. This I was missing this gamma in the previous slide. Please correct it. So, this is Laplacian square in terms of zeta, y and z of phi is equal to minus gamma q delta r in terms of zeta, y and z. This is like the potential of a point charge. Therefore, I know the solution. The solution for phi therefore is going to be phi zeta y z, there is a divided by epsilon 0 divided by epsilon 0 here, is equal to 1 over 4 pi epsilon 0 gamma q over square root of zeta square plus y square plus z square. And when I substitute the values of zeta, this comes out to be 1 over 4 pi epsilon 0 gamma q divided by gamma square x minus v t square plus y square plus z square raised to 1/2. That is the solution for phi. So, we have solved this equation for uniformly moving charge. We have solved the equation del square phi minus 1 over c square d2 phi by dt square equals q delta x minus v t delta y delta z, and the solution for this equation is phi x y z t equals 1 over 4 pi epsilon 0 gamma q over square root of gamma square x minus v t square plus y square plus z square. Next, we solve the vector potential equation, and that equation is del square A minus 1 over c square d2A by dt square equals minus mu naught q v delta x minus v t delta y delta z in the x direction. In exactly the same manner, You can go about solving this equation also. One thing you anticipate is that A is going to be A x, y, z, t in the x direction. Then the rest of the solution is exactly like what we did for the scalar potential, and I can write therefore the solution as A vector x, y, z, t as mu 0 over 4 pi q v gamma over square root of gamma square x minus v t square plus y square plus z square. So, we have solved the Maxwell's equations for a particle moving with constant velocity along the x axis. So, solution for scalar and vector potentials for a point charge moving with constant velocity v equals v x are phi r t equals 1 over 4 pi epsilon 0 q gamma over square root of gamma square x minus v t square plus y square plus z square, and A r t equals mu 0 over 4 pi q gamma v over square root of gamma square x minus v t square plus y square plus z square. And now, we can calculate the fields from these very easily. The electric field E r t is given as minus grad of phi minus dA dt, and the magnetic field is given as the curl of A. I will leave the calculation for you to complete, and when you perform your calculations, you get E r t as equal to q gamma over 4 pi epsilon 0 times, I will write the other factor independently, x minus v t in the x direction plus y direction plus z in the z direction divided by gamma square x minus v t square plus y square plus z square raised to 3 by 2, and calculate B. That comes out to be v over c square cross E. As simple as that. I would like to leave the calculations for you. So, we have got these expressions for electric and magnetic fields for a charge moving with uniform speed. Let us see how do these fields look. We have written E as q gamma over 4 pi epsilon 0 x minus v t x plus, let me write for y and z as s vector using cylindrical kind of coordinates, gamma square x minus v t square plus s square raised to 3 by 2. We can simplify this using the definition of gamma. Gamma square is 1 over 1 minus beta square, where beta is v over c. So, I can write E as q gamma over 4 pi epsilon 0 x minus v t x plus s divided by x minus v t whole square plus s square minus beta square s square raised to 3 by 2, and I get a gamma cubed here. And this therefore becomes q over 4 pi epsilon 0 1 minus beta square x minus v t x plus s s divided by x minus v t whole square plus s square minus beta square s square raised to 3 by 2. Let me now make a picture and show you what these mean. Here is the charge q at a distance v t along the x axis. I am making this picture in the xy plane, and I am looking at a point x s. So, the distance out here is x minus v t, and this is in the lab frame, in our frame. So, I can write this x minus v t square plus s square as r square, where r is the distance of my observation point from the charge. Its instantaneous position is at v t, and the distance of the observation point from the charge from its instantaneous position is r. And therefore, beta square s square is beta square r square s by r square. So, the angle, if the angle between the velocity vector and the observation point is theta, I can write this as beta square r square sin square theta, and therefore, I can write E vector as q 1 minus beta square over 4 pi epsilon 0 r square, where r is the distance from the instantaneous position of the charge, times r unit vector divided by 1 minus beta square sin square theta raised to 3 by 2. So, the field is in the direction of vector from the charge's position to where I am looking at the field, and it has this theta dependence. So, let us see how does it look. So, if I were to plot it in the xy plane, and suppose the instantaneous position is at this point shown by blue dot. For theta 0 or theta equals pi, the denominator is large, and therefore, the field is going to be small. I am going to show the smallness of field by the lines being rare. So, the direction is still in the direction of where I am observing the field, but the lines would be rare. And as you go towards theta equals 90 or theta equals pi by 2, they become denser, because the field is stronger. Still points in the direction of observation, but it becomes stronger. Notice that it is symmetric about theta equals 0 and theta equals pi because of sin square theta factor. So, the field has changed a bit. The structure is still like a static charge. It goes from the point charge to the position where I am looking at the field, but it has spread a bit. It has become weaker along theta equals 0 and theta equals pi, but has become stronger on the other side at pi by 2 or 3 pi by 2. Keep in mind that the number of lines would remain the same because the Gauss's law is still valid. So, I still have integration E dot ds equals q over epsilon 0. So, q remains the same. The number of lines get redistributed, but the total number of lines or the total charge remains the same. Let us now look at the B field. BRT is given as curl of A, and if you do the calculation, this comes out to be V cross C square cross E. I have already plotted the E lines, and then from that I can calculate the B lines. So, here is the charge, and E lines are dense at theta equals 90, and they start becoming rarer as you go to theta equals pi or theta equals 0, and V is in the direction of the x axis. So, V cross E is going to be perpendicular to this plane, and those lines are going to look like this, and as you go farther, the lines are going to become, the field is going to become weaker and is going to be strong out here. This is how B field lines are going to look. So, they are like, in direction they are like that of a current carrying wire, except that the field becomes weaker and weaker as you go away from the charge. So, these are B field lines. I would like to ask you a question at this point, and that is, draw qualitatively the Poynting vector around charge and argue that the charge moving with constant velocity does not radiate. Let us now try to understand and develop a feel for these fields, why these factors of gamma and all these things come in. So, I want to interpret this. Let us first look at the electric field, which is q gamma over 4 pi epsilon 0 gamma x minus v t x plus, I have been writing s, divided by gamma square x minus v t square plus s square raised to 3 by 2. Keep in mind that all these distances are measured in the lab frame. So, here is my lab frame, and here is this charge moving. The distances are v t here, x minus v t here, and s, which is the perpendicular distance from the x axis. It's moving along the x axis, and this is y. Now, in the frame of the charge, the distances will be proper distances. So, if I am writing x minus v t in lab frame, it will go to gamma x minus v t in the charge frame. S will still go to S because this is perpendicular distance. I wrote an extra gamma here, I want to cut this. So, I can write that E that I am observing in lab is actually equal to Q x charge over 4 pi epsilon 0 x square plus s square raised to 3 by 2 in the x direction plus gamma q s charge in the s direction divided by 4 pi epsilon 0 x square plus s square in charge frame. So, here is the charge and I can write E that I am seeing in the lab frame RT as equal to Q over 4 pi epsilon 0 x charge frame divided by R square in charge frame in the x direction plus gamma q over 4 pi epsilon 0 s charge frame divided by R square in the charge frame in the s direction. The first term I am going to call E parallel in the charge frame, and second one I am going to call E perpendicular in the charge frame. By parallel and perpendicular meaning that E parallel to and perpendicular to the velocity direction. So, I can say that in the lab frame the parallel component remains the same as that seen in the charge frame, and E lab frame perpendicular component becomes gamma times E perpendicular the charge frame. So, what we have done essentially is that we number 1 sat in the charge frame, 2 calculated the field in the charge frame, and that will come out to be E, let me write charge equals Q over 4 pi epsilon 0 R unit vector charge frame divided by R square, and then third transformed the field components according to these rules, which we deduce from the formula that we just derived. So, I am now going the other way. So, you can see that I can think of this charge produced field as something which I either get directly by solving the potential equations or calculating it in the rest frame of the charge and then transforming. Relativity and these transformations followed after one learned about relativistic dynamics. These transformations were earlier derived, not these expressions were earlier derived by Lorentz, as I already said, and this actually opened the door for relativity. People do tend to derive these results from a transformation point of view, as I just said on the right side of the slide, but it's good to go over the original solution, because remember, relativity came out of electrodynamics. Electrodynamics was the first theory that was relativistically invariant, and that necessitated the need to understand this. Lorentz transformation and all these things were proposed earlier by Lorentz to explain the negative results of Michelson-Morley experiments. All this is a very interesting reading, and it's good to read the original derivations and original thinking, and then everything sits well together. So, the way we have understood this field due to charge is how the distance is transformed, but I still have this gamma factor for E perpendicular that I have to understand. I will try to understand this through the linear charge density. Remember, all these formulation of Maxwell's equations are done in terms of charge densities. So, somewhere if the density transforms when Lorentz contraction, length contraction takes place, that somehow has to figure into things. So, if I look at the field due to a line charge, if I take a line charge with line charge density lambda and make it move with speed v, then the charge density in the lap frame would become gamma times lambda because of length contraction. And if the charge density becomes more, then the perpendicular field, and in this case the field will remain perpendicular, that you can show and argue. Both E perpendicular would become gamma times E perpendicular charge frame. So, we explain this factor of gamma for perpendicular component again from length contraction. For all this, I would like to suggest reference which is the electromagnetic theory Berkeley Physics course, volume 2, written by E. M. Purcell. He gives a very nice discussion of all these transformations and relativity and a little historical perspective. So, please read that, and all these things will become very clear to you and also make you look at these things in a very, very different way. Let us now solve a problem involving fields for a charge moving with uniform speed in a particular direction. This is problem from Griffiths, chapter 10, problem number 31, and it says a particle of charge q is traveling at a speed v along the x-axis. Calculate the total power passing through the plane at x equals a at the moment when the particle itself is at the origin. So, what the problem is asking is, here is the particle, it is at the origin, it is moving with speed v along the x-axis, and I want to find out how much is the power that passes through this plane at x equals a. From the Poynting's theorem, we know that the power passing would be equal to S dot d A, where A is the area. and in this case area happens to be in the x direction. So, this will be equal to integration of S dot x, and since I know from whatever I did just now everything is symmetric about the x axis. So, I am going to write this as 2 pi s ds 0 to infinity, where s is measured in the direction perpendicular to the x axis. S is given as 1 over mu 0 E cross B, which in this case is 1 over mu 0 E cross V over C square cross E. So, S in this case is 1 over mu 0 1 over C square E cross V cross E, which is equal to epsilon 0. E cross V cross E is going to be E dot E V minus E dot V E. Remember, V is V x. So, I can write S as epsilon 0 E square V x minus E x V E. Therefore, S dot x is going to be epsilon 0, V I can take out, E square minus E x square, or epsilon 0 V E s square, or E perpendicular square. Now, I know that E s is q gamma over 4 pi epsilon 0 s over gamma square x minus v t square plus s square raised to 3 by 2 is the magnitude of E s, and I am given that x equals a and t equals 0, because this formula assumes the particle having passed the origin at time t equals 0, and therefore, I get the power which is integral s dot x times 2 pi s ds as equal to integration epsilon 0 v E s square 2 pi s ds, which will be equal to q square gamma square epsilon 0 v divided by 16 pi square epsilon 0 square integration s cube ds divided by gamma square a square plus s square raised to 3 by 2, s varying from 0 to infinity. Integral is very simple to do, and you do that and you get the answer v q square over 32 pi epsilon 0 a square. That is the power that is passing through that plane. Where is this power going? How is the energy conserved? That I will leave for you to think about. So, let me now conclude this lecture by stating that we wrote inhomogeneous wave equations for a scalar potential phi r t and vector potential A r t solved these equations in the Lorentz scale for a uniformly moving charge with velocity v. Thank you.